Hello, these are the video solutions for homework 1.10 for AP Physics 1 in the 2018-2019 school year. So, number 17 is a conceptual question, but we can explain it pretty well if we look at a diagram. So we fired two balls, A and B, fired from the ground with identical speeds. So let's start by sketching the ground. And they're fired with the same speed, but with two different angles. An angle A and an angle B. So let's just really quickly draw. Here's angle A, and then we'll say over here, we'll just draw it on top, angle B. So they're fired with the same speed, so we'll just call this speed V, or V naught even. And I want to know which reaches a higher elevation. Well, let's take a quick look at how their y components compare. So for A, so this is V naught A, and this is V naught B. If I look at this, if theta A is bigger than theta B, then that means that the sine of theta A is going to be bigger than the sine of theta B. Since they have the exact same speed, since these two are equal to begin with, then we can actually conclude that the V naught in the y direction for A has to be greater than the V naught in the y direction for B, because V naught y in both cases is going to be equal to whatever the V naught is times the sine of that angle. So because sine of theta is bigger and V naught is the same, V naught y has to be bigger for A compared to B. So which one reaches the highest elevation? Well, we figure out elevation based off of this formula. It's the third kinematic equation, if you recall, and we're looking for delta y. So like we've done in the past, if I isolate delta y as Vy squared minus V naught y squared over 2ay, and I think about the fact that at the top of my arc, right here, Vy is 0, then I can say that this is 0. And so this just simplifies to negative V naught y squared over 2 times, well, negative 10. So we can simplify once more and just see that delta y is going to be V naught y squared over 2. So we just said V naught y for A is greater than B. If we look at this and see that height is related to our initial y velocity, then we see that A will have to be greater than B. Therefore, so this is A, delta y, that looks like an A, delta y A has to be greater than delta y B. Now, which one stays in the air longer? Well, it kind of depends a little bit on what we just did. So we know that from the y direction that we're going to be in the air until we land again. So if I have these two different paths, you can just think about it and see that, okay, well, delta y is equal to V naught yt plus 1/2 ayt squared. And for us, we know that this would actually be 0 for delta y because we start and end at the same place. Our V naught y, we'll just leave as V naught y right now, and we're going to think about V naught y for A and B separately, times t, which is what we're looking for. And then we'll say, just like we've done in class, minus 5 times t squared. So there's two answers for this. I can just factor a t out. I have V naught y minus 5t and t. So my answers are t is 0. Okay, that's where we start. And then V naught y minus 5t is equal to 0. Or we can just say that t is equal to V naught y over 5. So I actually go ahead and see again that time depends on V naught y. So which one stays in the air longer? Well, it's the one with the larger V naught y. Therefore, we have to say that the time for A has to be greater than the time for B because the V naught for A is larger in the y direction. So which one travels further? Well, this also kind of depends on what we've just done. Let me change colors once more. So which one travels further? So in this case, I'm talking about delta x. So this one is actually a little trickier. And in order to do this, I'm going to draw one large graph, or not graph, I guess just a diagram. So here's my ground again. And here is a projectile. So I'm going to be launching with several different angles. So if I launch kind of in this direction, my path will be a parabola that looks something like this. If I lower my angle of launch with the same speed, I'm now going to have a larger Vx in the initial, or larger initial x velocity. So I'm going to go further this way, and I'll have a path that looks something like this. And that actually is maximized at 45 degrees. Now, that's important, right? Range, which is just a fancy word for delta x, is maximum at 45 degrees. Below 45 degrees, I'm going to have a case where I'm not in the air as long, but I have a greater x velocity. So I'm still going to have less range because I'm not in the air as long. So you can kind of see from these three cases that it's not necessarily true that A would be always greater or always less than B. So my conclusion here is you really can't tell, because range, right, depends on, like because range could have two different of the same range for a single, two different angles for the same range, because range can have two angles with the same result, is what I'll say. And that's okay. This is important to discuss. So we can explain a little bit with math, but it's all about comparing. Okay, how does this variable affect another variable? And then can we make an actual assumption about which one always travels further? No, we can't. So go look at your range equation and you'll see that. For question number 23, we have a hose that fires water at a speed of 6.5 meters per second. So I'm going to just draw on top of this that my V initial, or my speed, is 6.5 meters per second. And I want to know what angle or angles should I point the nozzle at, defined here as theta naught, in order to make sure the water lands 2.5 meters away. And why are there two different angles? So this right here, quick reminder, is delta x or range. Either one is an acceptable term. And we're basically saying that that is equal to 2.5 meters. So my range equation is V naught squared times the sine of 2 times theta naught, make sure we have that in parentheses, over g. So quick reminder that g is actually just the value, not negative. So it's not going to be negative in this case. It's only negative when I need an acceleration. So g by itself is not necessarily the direction that I want. So when I go into this and I calculate for a range of 2.5 meters, actually let me rearrange this equation over g. So I'm trying to solve for angle here. So I'm going to multiply by g, and I'm going to divide by V naught squared, and that's going to be equal to the sine of 2 theta. So I know that 2 times theta is actually equal to the inverse sine of this ratio, range times g over V naught squared. So let's actually go ahead and plug in some values here. So 2 theta equals, so we have r, which is 2.5, times g, which is 10, over my initial speed of 6.5 squared. Oop, and I actually forgot the inverse sine part, so let me go ahead and rewrite that. So sine of this, and that's equal to 2 times my initial angle. So what I get out of this is an angle of 36.3 degrees. So 2 times theta is equal to 36.3 degrees. So very easily I can say, all right, well, theta has to be half of 36.3 degrees, which is 18.1, or just 18 degrees. I'll just say 18. So there's one of my answers. It's very obvious. Now the part that's not obvious is that when I use the inverse sine function in my calculator, it actually is only going to be giving me 1/2 of the real picture. And the reason for that is, if we have a unit circle, so my sine function is talking about my opposite over my adjacent side. So if I remember my unit circle, then there's a value here. So this is y and x, and this is, in this case, the hypotenuse. There are actually 2 different values, so let's call this r, which is 1. And then there are 2 different values for which I get the exact same sine. So there's this angle and this angle. And in both cases, y is the exact same, r is the exact same. So the sine of my angle is actually going to be the exact same. So there are actually 2 different values that I get. 1, which is in the first quadrant, and 1, which is in the second quadrant. So my second quadrant is just going to be a mirror of this. So let's see. I got out of this 36.3 degrees. So if I say that this angle right here is 36.3 degrees, then that means that this angle is actually 180 minus 36.3 degrees. And so 180 minus the 36.3 is 143.7 degrees. So my other answer actually comes from the fact that 2 times theta naught is also equal to 143.7. So my other angle is half of that, which is pretty much 72 degrees. So what we just kind of saw actually helps us with another bit, which is that no matter where I would be in the second quadrant from my other answer for the angle, I have to end up in the first quadrant because I'm still shooting the water to the right. So in the end, I have to shoot at some angle off to the right. So what that means is I don't necessarily need the supplementary angle to work from. I can actually just work with the complementary angle of my final answer. And so you can actually see that these 2 together would add up to be 90 degrees as a complementary angle. So anytime that I have this situation where I'm finding an angle to launch from, I will get 2 different angles, unless it's 45 degrees, 2 different angles that have to be complementary. For question number 27, it says we fire a projectile with an initial speed of 36.6 meters per second at an angle of 42.2 degrees above the horizontal on a long, flat firing range. So I'm going to draw a quick sketch of this. Here's my range. And I'm firing a projectile from the ground with a speed of 36.6 meters per second. And I'm firing it at an angle of 42.2 degrees. And this is long and flat, so that means that if we land, we're going to land at the same altitude. So part A says I want to find the maximum height reached by the projectile. So I'm working on this path. So to figure out where I end up, I know that I'm going to be looking for a delta y, and I'm looking for it at the highest point. And so at the highest point, I know that Vy is 0. So I'm going to take my initial velocity, and I'm going to find V naught y to begin with, which is going to be V naught times the sine of this angle. So V naught y in this case is going to be 36.6 times the sine of 42.2. So V naught y for me will be 24. I'm going to go ahead and keep it all the way to 0.58. So this is my initial velocity in the y direction. So I know this initial velocity, I know a final velocity, I'm looking for delta y, and because I am dealing with a projectile here, I know that my y acceleration is negative 10 meters per second squared. So with these 4 bits of information, I can go on to use the second kinematic equation to solve A. So delta y will be equal to v naught y, or I don't want to use the second kinematic equation, I'm sorry, I got ahead of myself. I want to use the third, because vy squared is going to be equal to v naught y squared plus 2 times the acceleration in the y direction times the y displacement. So solving for the y displacement, I have vy squared minus v naught y squared over 2 times my y acceleration. Substituting values, I know that this is 0 minus my initial y velocity, which I just found to be 24.58. Don't forget to square it. Over 2 times negative 10. So when I go in and evaluate this, the highest that my projectile goes is 30.2 meters. So B asks me for the total time in the air. So for the total time in the air, I want to go from this starting position to this ending position. And remember, time depends on the y, or the vertical motion, of my object. So from the beginning here to the end there, my delta y is 0, because I start and end at the same height. My acceleration is still negative 10, and my initial velocity is still 24.58. Now I would like to use the second kinematic equation. So delta y is equal to v naught y times t plus 1/2 my acceleration in the y times t squared. So substituting some values, I have 0 is equal to 24.58 times t. And then I'm going to go ahead and say minus 5, because that's 10 times 1/2, or negative 10 times 1/2, times t squared. So this is easy to solve. I can factor out 1t, and I have 24.58 minus 5t and t. So now I have a solution where t is 0, which is where I begin. So that's one location where my displacement was 0. And my other is going to come from saying 24.58 minus 5t is equal to 0. So if I solve this for t, I find that t is going to be equal to approximately 4.9 seconds. And so that's how long I'm going to be in the air. So let's go back and look up at what c is. So c says the total horizontal distance covered. That is the range. So I can do this 2 different ways. One is I can go and find, so there's 2 ways. One is I can go and find delta x based off of the fact that I know that I'm in the air for 4.9 seconds, and I can find v naught x, because that will be v naught times the cosine of the angle. And then I can simply use delta x is equal to v naught x times t. So this is one method. The other is we can use our range equation that we just found, as range is equal to v naught squared times the sine of 2 times my launch angle over g. So let's go ahead and use this so that I don't have to do any calculations for v naught x. So r is going to be equal to v naught. So this is my initial speed. So keep in mind I wrote v naught is 36.6. So I have 36.6 squared times the sine of 2 times 42.2 degrees over g, which is just 10. So when I go ahead and calculate this, my range, or my maximum x displacement, is 133 meters. So not too bad. We just straight up use this equation and we can find that range. Now, for D, I want to know the speed of the projectile after 1.5 seconds. So let's actually go up here and take a look. So after 1.5 seconds, where am I? Well, I found that I was in the air for almost 5 seconds. So 1.5 seconds later is going to be somewhere on the up. So I want to know this speed right here. In order to do that, I need to know Vx at this location and Vy. So we need to find those two components after 1.5 seconds. So D, I need to know Vx. Well, that's easy. Vx is going to be equal to V naught x plus AXT. Well, the acceleration in the x direction is 0, so that's 0, which means Vx is equal to V naught x. Well, V naught x is equal to V naught times the cosine of my angle, or my initial angle, I should say. So Vx in this case is going to be equal to 36.6 times the cosine of 42.2 degrees. So Vx is going to be approximately 27.1 meters per second. So there's one component. Vy is going to come from the exact same equation. It's going to be equal to V naught y plus my y acceleration times time. So Vy is going to be my initial y velocity, which I found to be 24.58, plus a negative 10 times the 1.5 seconds after which time has passed. So Vy in this case is going to be 9.58 meters. Or meters per second, sorry. So these are my Vx and my Vy. I want to know the speed. So remember, this is a triangle. So here is my V, here is my Vy, here is my Vx. So V squared is going to be equal to Vx squared plus Vy squared. So using the Pythagorean theorem here, I have the square root of 27.1 squared plus 9.58 squared, pardon the 8. And solving for my speed, I get 28.7 meters per second. So there is my speed of the projectile. And that's the end, because I don't need the angle at that particular instant, but I had to use the first kinematic equation to find my components at some particular time. For question 55, we have a jumper who is capable of jumping 8 meters. So we're going to assume that he is jumping as a projectile. And so here is my ground. And he jumps, and he goes a distance of 8 meters. So my delta x in this case is equal to 8 meters. Now, his horizontal speed is given to be 9.1 meters per second as he leaves the ground. So I'm going to write over here that V naught in the x direction is equal to 9.1. So now I want to know how long is in the air and how high does he go. So I want to know t, and I want to know delta y right here. So I'm going to start with finding t. So for t, I have v naught x, I have delta x. I know that because the x acceleration is 0, that v naught x times t is going to give me delta x. So time in this case is just going to be delta x divided by v naught x. So that's going to be my 8 meters over 9.1 meters per second. So my time in the air is going to be only about 0.88 seconds. Okay, that's the time in the air. Now the question is, how high does he go? Well, there are a couple different ways to do this, but what we're going to do to make it easiest is we're going to rely on the fact that this is a symmetric path. Now what I mean by that is that the time spent moving upward is going to be equal to the time spent moving downward. And so in my diagram, That's going to be, this is my t up, and this is going to be t down. So why is that useful? Well, that means that together, that has to be equal to t, because half is spent going up, half is spent going down. So I know then that t up and or t down is equal to, well, they're equal to each other, which is going to be, in this case, 0.88 divided by 2, or 0.44 seconds. So what do we do with this information? What we can do is we can remember that at the highest point, Vy is equal to 0. So let's actually look at the part where I'm going downward. So when I look at the portion where I'm going downward, I know that delta y is what I'm looking for. I know that the acceleration of y is -10. I know that the time spent, so I'll say downward, is 0.44 seconds. And I know that Vy is actually my initial velocity. So think about starting at the top. And that's going to be 0. With these 4 bits of information, I can use the second kinematic equation in the y direction, and I will be able to solve for delta y. So v naught y we just said is 0 times time, so I'm not going to write that, 0.44, minus, well, -10 times 1/2 we keep saying is -5, and then minus 5 times 0.44 squared. So the delta y, which is how high up I went, has to be, in this case it says -0.97 meters. Well, I don't really care about the negative bit because remember I started here and I went down, right? So I just care about the fact that the maximum height is the 0.97 meters, which, if you think about it, actually makes pretty good sense for a long jumper. They are only going about 1 meter into the air in order to actually travel 8 meters horizontally.